Hello guys, welcome back to my channel Gamma Di Gamma. In this video, I'm going to be doing some physics for a change. So it's all about pendulums, but instead of hand waving like you will do in most introductory mechanics courses, I will try to keep that part to the minimum. And of course, if you have any questions, please let me know in the comment section. So now let's get started. First of all, we have the equation for a pendulum system. So we have a pendulum, which is basically has a bob on a string, which is massless. Now, the bob has mass, not the string. A bob is just a concentrated piece of mass. Now the weight of this bob is acting down, mg. Say it's at an angle theta, then the sine theta of the weight is actually going to be the restoring force, of course, times the L for the sake of dimensions. So the force on the the acceleration is ml squared theta double dot. Now when I use the dot notation, it's the time derivative. So two dots is two time derivatives. So this is d2 theta over dt square basically. And we have the restoring force, but the restoring force is only taking it back towards negative angles. Now one more point is I'm measuring in throughout this video angles in the counterclockwise sense. So, 0 will be basically if when the red string is basically lying coincidentally with this white one. And then 90 will be when it's perpendicular to the this white base. So the restoring force is basically taking it back to lesser angles. So that's why it's a negative here. Now the second derivative of theta is equal to minus gl sine theta. Theta double dot plus g over l sine theta equals 0. I've just cancelled constants out. Now at this point, given the initial conditions of, an initial amplitude at t equals 0, theta is alpha. So it starts with an inclination alpha and theta dot is 0. So it has no angular velocity. It's because it's being held at time 0, and then you let it go and then it starts doing whatever the physics it does. Now we all know what the physics is. It's going to be a simple harmonic oscillation. But in this video, I'm going to show you that, that's just the leading order term. It does way more interesting things. And for that purpose, I'm not going to be using the small angle approximation. So at this point, you would just say that, well, theta is small, sine theta is just theta, and then you have a second order linear differential equation in theta, which you can solve. The solutions are sines and cosines. G over L, you call it as omega squared, where omega is the natural frequency. I will write that later. But in this video, I'm not basically just going to conclude that. One thing we can do from this point, because we're not, using the small angle approximation, is we can multiply by a theta dot. This is a trick by Newton. You will see this a lot for these systems where the total energy is conserved, and I will come to that point again. Because if I do that, then I can write theta dot and theta double dot as 1/2 theta dot squared derivative of that. You can check by the chain rule that you will indeed get the theta dot and theta double dot term. Similarly, I can write the sine theta theta dot as g over L minus cosine theta, because again, if you differentiate, you'll get basically what we had on top. All of that equals 0. We won't be able to do this, if the potential, this is the potential term because it doesn't have any double derivatives. We wouldn't have been able to do this if this sine had no antiderivative. If this function, it may not be a sine for a more complicated system. If that didn't have an antiderivative, then we wouldn't have been able to do this, and then all of this would just fall flat. And that's why conservation is important, which is, again, I'm really teasing you on this. I'm going to come to that point later. So now we can just group the derivatives using linearity. we get 1/2 theta dot squared minus g over L cosine theta, quantity equals 0. Okay, and I'm just defining omega as square root g over L here for future reference. Now from this we know that this quantity inside the square brackets, 1/2 theta dot squared minus g over L cosine theta equals a, which is some constant. It's a constant that is, independent of time, because the time derivative was 0. If we just multiply by ml squared again, the factor that we cancelled initially, 1/2 ml squared, and also the 1/2 ml squared plus mgl 1 minus cos theta. So I'm actually adding and subtracting an mgl here. So adding here and grouping it with the cosine and then subtracting it here equals aml squared. Now if I group all this, 1/2 ml squared theta dot squared plus mgl 1 minus cos theta equals E, where E is a ml squared plus mgl, which is basically a constant in this system because a is a constant, we know that. ml squared, mgl, all of these are constants. The mass of the system remains the same. The length of the string is also the same. Otherwise we would get a nonlinear differential equation. I mean, we do have a nonlinear one right now. It's just this one would be way harder to deal with. And that's not the purpose of this video. That's for parametric kinds of differential equations. Anyways, so the point is that this first term is the kinetic energy. You can check that. mgl times 1 minus cos theta is actually the potential energy. Now I'm being careful because a potential energy, it depends on what you define as your ground, because you need the height above whatever you consider zero potential. Now zero potential for me is basically the height that this bob, when this pendulum is basically just vertical along this line when theta is 0, that height of the bob, that height of the center of mass, is position of the center of mass, is basically what I'm considering to be zero potential. So anything that's above that, it's going to be 1 minus cos theta, because cosine theta is actually going to be just the projection along this this vertical line, and we want how much above the ground it is. So it's going to be 1 minus cos theta, rather with the L. So L times 1 minus cos theta is going to be that length above that ground potential. So that's going to be the total potential. I mean, depends on what you consider to be your zero potential. According to that, you wouldn't have an mgl if you considered zero potential basically to be just just this length rather than this length. Anyways, this E is actually the energy of this system. So conservation of energy, we have, it's just the statement of conservation of energy, and all of this is a result of time translation symmetry. This is because of Noether's theorem, which says every symmetry corresponds to a conservation in the most simplistic terms. I mean, of course, there's two statements which I may prove in a future video, but for now, this is all we need to know. And again, for just to know where we got this expression, it's because the sine theta had an antiderivative. The kinetic term, it's basically always there. The physics of the system really depends on the potential, because you change the potential, you change the physics. You make this into hydrogen potential, then it's going to be the spherical harmonics, for example. So that it depends on whether that potential has an antiderivative with respect to time, whether it's integrable with respect to time. And that basically is because of time translation symmetry, that in this equation, if I change times, if I change time from t naught, if I change time to t naught plus alpha, which is basically like if my physics is like a video, I skip forward by t naught plus alpha, and my video, I jump forward to an identical moment. I can't distinguish between the physics then and the physics before I skip to time alpha. is what I mean by time translation symmetry. This is basically a consequence of that. Now, enough of that. Again, the consequences of this Noether's theorem, which is an excellent theorem, are many. Here are some. It's because we know that this quantity is a constant, right? I mean, we have it here. It's a constant with time. So that means the quantity evaluated at any time equals the quantity evaluated at any other time. So that means the quantity evaluated at time 0 equals the quantity evaluated at any arbitrary time. Now at time 0, we have the initial conditions that the angle has to be alpha and the velocity was 0. So only term we have is minus g over L cosine alpha and 1/2 theta dot squared minus g over L cosine theta. We can rearrange 1/2 theta dot squared equals g over L cosine theta minus cosine alpha. Now theta dot squared, well, is a square, so it has to be greater than or equal to 0. So that gives us cosine theta is greater than or equal to cosine alpha. Now the domain, let's look at the domain. So on theta, which is between 0 and pi over 2. Now the domain of theta in all is minus pi over 2 to pi over 2, because with the pi over 2, you're going to be perpendicular to this vertical reference line, and minus pi over 2 is basically the other side. That's the extremities, otherwise we would have a reflex angle, and we don't really want to, technically, sorry, an obtuse angle, and we don't really want to consider those because that borderlines towards chaotic motion anyways. So on the interval 0 to pi over 2, cosine is decreasing. You know the graph of the cosine. So that means if cosine theta is greater than or equal to cosine alpha, that means theta is less than or equal to alpha. Fair enough, because it's decreasing. That's just the definition of decreasing. And negative theta is greater than or equal to negative alpha. I'm just multiplying by negative, that flips the inequality. And if theta is between 0 to pi over 2, we know minus theta is between negative pi over 2 and 0. So all in all, if theta is between minus pi over 2 and pi over 2, we know that it's going to be between minus alpha and alpha. All right, because if it's in the first domain, it's upper bounded by this alpha, and if it's in the other domain, if it swings back towards in a negative angle region, then it's lower bounded by a negative alpha. So all in all, we have minus alpha less than equal to theta, which is less than equal to alpha, and these alphas basically become the amplitude. That this just shows that at any point during the the physics of this system, the motion of this system, the pendulum isn't going to exceed alpha. So in a way it's constrained, and all of that is a consequence of this conservation of energy, which is a result of time translation symmetry. So it's very elegant, and I wish they would really teach these things very holistically. And it's not just because we made a small angle approximation and that's why we know the amplitude fixed. It's actually fixed just for this system, just for this potential which characterizes the system. Okay, now let's actually try to solve and evaluate this problem. So we have this equation where a is a constant. Now we're finally going to plug in omega equals square root g over L. So we have 1/2 theta dot squared minus omega squared cosine theta equals negative omega squared cosine alpha, which is basically the value of a, from before. See, from before. Anyway, so theta dot now, to consider both branches of the solution, is plus or minus square root 2 omega times square root of cosine theta minus cosine alpha. Now, what about the convention? Well, we're still following the same convention as I said. So when do we consider theta dot positive? Well, if it's swinging towards greater thetas, if the pendulum swinging towards increasing angles, the theta is positive. If the pendulum is swinging towards lesser angles, it's negative. So let's say, because I'm right-handed, I start with here at amplitude alpha, and I swing. So I'm going to be considering the negative branches. right? And again, these solutions are going to be periodic, because once it completes its negative branch by reaching the other point, we're going to have to pick the positive branch to swing the other way. So in a way, the solution is going to be piecewise, just because of this square root branching thing. So let's consider the negative solution, just because I'm right-handed. We have a 1 over square root 2 omega with a minus integral from alpha to theta. So I'm considering oscillation or the motion from alpha, which is the initial position, to an arbitrary angle theta. And again, that arbitrary angle has to fall within the negative swing, the negative theta dot swing, the branch of the solution. Because if it doesn't, then we have to consider the positive, and then we have to add the initial swing and then add the positive back, if it's if you want to consider when the bob swings to the other extreme and then comes back for that position again. So let's just consider simple case where theta is just between in its first swing, it's basically between this alpha and over here somewhere. We're just considering the first time the bob is at position theta, and that time at where it actually lands on theta is we can call t, for lack of better variables. And of course the time is 0 when it's at alpha, because that's where we sort of let it go, the initial conditions. Now we can use this formula, the half angle formula of the cosine in terms of the sine. So cosine phi is 1 minus 2 sine squared phi by 2. Why does that help us? Because we can sort of write the denominator argument of the square root as sine squared alpha by 2 and sine squared theta by 2, all equal to t. And we also get rid of the square root outside, which is nice. Now with a nice substitution, x equals sine theta by 2 over sine alpha by 2, and we have the corresponding dx using chain rule. We know that that t is 1 over omega x naught to 1. Well, x naught is the appropriate lower bound. Well, it'll actually be, if you plug it in, it's going to be sine theta by 2 and over sine alpha by 2. I'm just calling it x naught. 1 over square root of 1 minus x squared sine squared alpha by 2 times square root of 1 minus x squared dx. I keep simplifying every step, I just, and then I'm going to break this x naught to 1 interval as 0 to 1 minus 0 to x naught. Why is that? Because the first guy we can write as the complete elliptical integral of the first order, evaluated at sine alpha by 2, with of course the 1 over omega prefactor, minus 1 over omega times the incomplete elliptical integral of the first kind, evaluated x naught colon sine alpha by 2. So I'm going to write down what these guys are. So k of k, which is the complete elliptical integral of the first kind, and I made a video on this, so please check that out, is integral from 0 to pi over 2 d theta over square root 1 minus k squared sine squared theta, or 0 to 1 dt over square root 1 minus t squared times 1 minus k squared t squared, which is basically what we're using. This is the second one, is what we're using here. Now f of phi k is the incomplete elliptical integral of the first kind, which has two forms. Either you write the phi with the comma with the second argument, like this 0 to phi d theta 1 square root 1 minus k squared sine squared theta, which is an analog to this guy. It's just that the upper bounds here were fixed. Here it's a variable, which is the first argument. Or you write it with the semicolon like this, x semicolon k, which is the form that we require, which is a shout out to the second form. Instead of the 1, we have an arbitrary variable x here. That's the only difference. So you see, that's basically the solution, the arbitrary solution. And then this was for an arbitrary time. If you want to solve for the position, well, then you're going to have to evaluate this integral. You get an antiderivative, because x naught, although it's definite, x naught, it actually has a theta independence in there, because x naught is actually sine theta by 2 over sine alpha by 2. You're going to have a theta expression here ultimately, And then you're going to have to invert the theta expression if you want to solve for theta as a function of t, which is very, very tedious and, not really that insightful for now. I'm sure there's people who've done this kind of problem, but I don't think there's elementary solutions that exist for this. The more interesting question is the time period, though. We actually can find a nice form for that. Now, if we were to consider the half angle here, we would have the sines and cosines as, nice solutions. Cosine omega t, sine omega t, with the additional additive constants. And it would be all nice because it would be a linear differential equation. We form a vector space of the solutions and, so on and so forth. Linear algebra kicks in, which is always nice for linear differential equations. Now, as I said, the more interesting thing is the time period. Well, again, now to measure the time period, we start at some initial point, we're going to break the calculation in 4 parts. So the first part is, integral from the alpha to 0, which I'm going to call t1, the time taken from alpha to 0. Then the time taken from alpha to negative alpha, 0 to negative alpha, apologies, as t2. That's just half the period because it has to come back. So minus alpha to 0, that's t3. And then 0 to positive alpha, that's t4. So on 1 and 2, we have the negative branch because we're going back, we're going towards decreasing theta. And on 3 and 4, we have the positive branch. So t1 is integral from 0 to t1 is negative 1 over square root 2 omega integral of alpha to 0 d theta over, the square root cosine theta minus cosine phi alpha. So if we change theta to theta minus alpha, we get the upper bound 0 to minus alpha, and everything else is basically the same, which is basically t2. So t1 equals t2. Nice, that's good to know. That's the negative branch. Now for the positive branches, t3 is 1 over square root 2 omega integral minus alpha 0 d theta over the integrand. If we do a change, theta goes to minus theta, we actually see that this is t3 is actually equal to t1, the same integral as t1. So that's also interesting. And similarly, t4 is basically t1. Nothing needs to be really done. So all we have is the complete time period, which is t1 plus t2 plus t3 plus t4 is 4 times t1. So t1 is just 1/4 of the entire time period t. Okay. So t1 is t by 4. And then we have the integral. So 1 over omega, integral 0 to 1, 1 over square root 1 minus x squared sine squared alpha by 2, square root 1 minus x squared dx. And the lower bound was actually 0 this time. In the earlier case, in the arbitrary case, we had an x naught here, and that's why we had to break it up into an incomplete and a complete elliptical integral of the first kind. So we have 0 because we had 0 because the limits were going from alpha to 0. So with the alpha, we had the upper bound, and with the 0, the theta 0, we have the lower bound 0 to 1. So that just becomes the elliptical integral that we know and love. And that's basically the answer. So 1 over omega k times sine of alpha over 2. But again, this, you can find this in any pretty advanced textbook, and you would say, well, what's your contribution? My contribution is not that much. It's quite humble, but I think it's nice. So 1 over square root of 1 minus x, what we can do is first expand. If we can expand this term in terms of like a Taylor series, we can seem to approximate it. So we can write the 1 over square root 1 minus x is 1 minus x raised to 1 negative 1/2, and which has a nice Taylor series about 0. The Taylor series is, sum from n equals 0 to infinity 2n factorial over 2 to the 2n over times n factorial squared times x to the n. Now, I had some double factorials initially. I have just simplified everything for you. If you were interested in seeing the formal derivation of this, which is, not that, it's not that difficult, let me know. I will inform you. So now we have, instead of x, we have k squared x squared. So just plug that in here, which is fine. And remember, k is sine of alpha over 2. So t1 is basically going to be 1 over omega. Now we have the integral of this infinite sum. And you might say, well, you don't argue well for when we interchange these things. You just willy-nilly interchange them all the time. Here's the argument. Well, actually, if you look at the power series here, it's actually within its radius of convergence on the domain of x, which is from 0 to 1. So x less than 1 is the radius of convergence, because if x equals 1, it's anyways not defined, because 1 minus 1 is in the denominator. So that it's in the radius of convergence. Power series in its radius of convergence is uniformly convergent, and therefore, uniformly convergent by the Weierstrass M test. And from that, if the terms of the sequence of the power series, which the power series forms, the sequence formed by the power series, if those terms are integrable, then the entire power series is integrable, which is why we know that this quantity here, which the partial sums of the power series which form the sequence, they're all integrable, because x to the 2n is continuous. Continuous functions are integrable. Therefore, everything is integrable, and then we can just interchange the sum and integral. I urge you to read some literature on this. So u equals x squared, du is 2x dx. Now we can actually go ahead and actually simplify this. We get integral from 0 to 1 minus u to the negative 1/2 u to the n minus 1/2 du. And remember the definition of the beta function, right? We identify the first argument with the power of 1 minus u, which is negative 1/2. So we get this, and then we have the second argument, which is 1/2. So we have 1/2 beta of n plus 1/2 comma 1/2, and k again is sine of alpha over 2. We can always write the beta in terms of the gamma functions using this nice identity, gamma of m times gamma of n over gamma of m plus n equals beta of m comma n. And we get this gamma n plus 1/2 gamma of 1/2 over gamma of n plus 1. Now gamma of 1/2 we all know is square root pi. That's beside the point though. If we write a few terms of this this infinite series, because all of this is equal to the time period, right? 1/4 of the time period. We're going to have 1/2 beta of 1/2 comma 1/2 plus k squared by 2, 1/2 beta of 3 by 2 comma 1/2 plus 3k to the 4th over 8, 1/2 b to the 5 over 2 comma 1/2, and so on. So it's increasing powers of k. Interesting thing is, if we compare them to the energy eigenvalues of quantum simple harmonic oscillator, the nth energy of the nth state is h bar omega n plus 1/2, where n is going from 0 to basically 0, 1, 2, the integer wise. You think this is a coincidence? I think not. It's because the structure of phase space is more or less preserved during a quantization process, and the quantization of the harmonic oscillator is a pretty well understood situation. We can actually calculate beta of 1/2 comma 1/2. It's just, you have this, you do a trigonometric substitution, u equals sine squared, you get 2 sine theta cos theta over cos theta sine theta d theta, which just results in pi. Interesting thing is, now if we sort of do a limit of small angle limit, so as k equals sine of alpha over 2 is small, alpha is small, which is basically a small angle approximation there, and therefore we can ignore the higher order terms in k, because k is, if it's less than 1, then we can really ignore them. It's really small. We can ignore the k squared, k to the 1, k to the 4th power and everything. Leading order of k, the leading order of k is just going to be the first term which had no k on it. So the first term which had no k, because you see it's increasing by powers of 2, so k squared, k4, k6. So the leading order is just going to be the leading term, which has no k in it. Alternately, you can just take the limit as k goes to 0, which is essentially the small angle limit, the limiting case. You get 1 over 2 omega beta of 1 half comma 1 half, and that's where we need this lemma. We get pi over 2 omega, which is time period is basically 2 pi over omega, which is 2 pi square root L by G, which is basically the well-known formula in the limiting case. So maybe I should mark this with a naught, which is the limiting case. There you have it. That's this video, guys. Thanks a lot for watching. I hope you enjoyed it. I particularly found the beta function in this form, the n plus 1 half, n being in integer from 0, very very illuminating and also interesting because it relates nicely to the eigenvalues, the energy eigenvalues of the quantum harmonic oscillator. And yeah, I think it's a very very nice problem. Let me know if there's any questions, or if I've waved my hands too much in any particular area. I try not to get into too much detail that detracts from the beauty of this particular problem in physics. Thanks for watching. Peace out, and see you next time.